Hey everybody, Mr. Plantt here, and today we are going to be going over our Unit 1 test review. We've got the Unit 1 test coming up next week, so we got to make sure that we're ready for the test, and then we're going to go through and make sure you're studying for it. Now, the way I'm going to do this is I'm not going to write out every single answer. I might draw some pictures and kind of draw some keywords, but it's going to be up to you to use what I say and what you hear and what you see to make your own answers out of it. So it should be a way for you to check that your answers are correct and maybe add on some information you might be missing. All right, so let's start with atomic theory. So Democritus, right? This guy, Democritus. Who was he? He was a Greek philosopher that lived about 2,500 years ago, and he theorized that everything in the world was made up of building blocks. So you can see I'm kind of drawing these bricks, right? Everything was made up of building blocks called atomos. All right, that's kind of where we get our name for the atom. Right? He said everything's made up of these very, very small things. They're indivisible. Atomos comes from the Greek word indivisible. And you can't get them any smaller, and that's that. And it didn't really build too much more. It kind of stopped there until we get to Dalton. Right? John Dalton came along and said, hey, I actually think that the way it works is we have this thing called the atom, and it's really this very circular, small object. Very, very small. And that it's just a solid chunk, a solid ball that kind of does things. Now, the model itself is pretty simple, right? Just billiard ball is what we call it, but it's just a solid ball. And so the big reason why this is no longer correct is that it doesn't include things like positive and negative charge. So no positive, negative charge. There's too much space taken up, so like no empty space. Remember, we found out through some experiments later on that the atom is mostly empty space, and so there's no empty space, and that's no good. All right, Thomson. So I'm going kind of fast, right? There might be other details that you could add. Remember, you can always go back and check the models of the atom video we did, or check your notes and add information from there. But I'm just trying to hit the main things, main ideas. Okay, Thomson's model of the atom was the plum pudding. So is this one that kind of is this amoeba shape, where most of the stuff in there, let's say this red stuff, is positive, and then the purple stuff are these negative chunks of electrons. And that they're just kind of all randomly in there like a big soup. That was the big idea with Thomson's plum pudding model, right? That it was big chunk of positive energy, or not energy, but big chunk of positive stuff. We don't really call it anything, with negative things called corpuscles, or now we call them electrons. Okay? And the big thing that was wrong, why we don't consider his anymore, is that it's the electrons, right? It has to do with the electrons. They don't sit in this kind of pool of positive stuff. They actually are rotating around a small nucleus, right? So the electrons are stuck in the middle. We still don't have the empty space, right? We still have that problem of empty space. Atom still is taking up too much space, and that's not how it actually works and how it makes things that we've observed work out. All right. Rutherford. Now this one, remember we did, if you can remember, let's see if I can draw it right. We did the 3 cups on the table. These kind of look like volcanoes, right? And we rolled marbles towards them. That was our Rutherford experiment. Okay, so Rutherford's model, let's highlight his name so we know it's important, right? Rutherford's model of the atom was also called the planetary model, and that's where we have this kind of small nucleus in the center, and we kind of started to get an idea that there's these positive protons in there and neutrons, and then we had electrons that just kind of exist around the nucleus, kind of in this planetary model. There wasn't really rhyme or reason to it. They just moved around, or they just kind of flew around the nucleus. Okay, and the big way that he discovered this is he took gamma rays, or not gamma rays. Who am I talking about? He didn't take gamma rays. He took beta particles, right? Different type of radiation, not gamma. He took beta particles and he shot them to a piece of gold foil. Right? Shot it, and then he went and observed how the beta particles reacted. And while most of them went through in a straight line, he noticed that every now and then some of them would deflect. And the ones that deflected were showing that it was hitting something, but that most of the time it was hitting nothing. So that's kind of the idea that we got mostly empty space. So I guess I drew my picture in the wrong spot. Here, we'll just do this. Aha. All better. Okay, so it was mostly empty space. So experiment, shoot beta particles at gold foil, measure where these, kind of in the circular screen fashion, measure where the atoms go, or the, not the atoms, the particles go, and then just kind of make some observations from there. So we saw that most went straight through, mostly empty space, some bounced off, so they were hitting something. Okay, a little while later, we have Bohr come along, and he is where we get probably our most accurate model of the atom for that time, right? We have more accurate models, but this one was, we'll draw a picture over here, right? This is where we had protons, which will have these little green dots. We had protons in the nucleus, that center area. We had neutrons, these little blue dots. And then in energy levels, we had electrons. And they're floating around in orbitals, or these energy levels. And these energy levels, remember that the lowest energy is the inside ring, the highest energy is the outside ring, and these electrons will hop from inside to outside rings and outside to inside rings, changing their energy, giving off photons, all sorts of stuff like that. Now, is this the most accurate? No, right? This is the easiest to represent, but technically the most accurate is the electron cloud model, where instead of rings, we just kind of have these fuzzy areas around the nucleus where we say these electrons are likely to exist, right? It might be there, maybe it's in this area, right? We kind of get these clouds around the area where those electrons most likely are, but we have no way of knowing. We just have to guess. We have to have a really educated guess, but we have to guess. All right, this is my favorite part. Drawing a electron releasing energy in the form of light while moving to different energy levels. So I'm just going to draw a really simple nucleus. We'll learn more about protons and neutrons and electrons in detail after our test, but right now we'll just do this, and we'll keep it simple with two. Okay, those circles suck. Let's redo this. That's not much better, but whatever. Okay, and so we need to remember that these energy levels, the outside one is the high energy, right? High energy, and the inside orbital is the low energy. Okay, and so our electron, to release light, it needs to start at a high energy shell and move to a low energy shell, or energy orbital, or energy level. There's a million names for this. Okay, and when it moves to that lower energy level, it is going to release a photon, right? And that is what we see. That is the light that we see with our eyes. Because this electron lost energy, the energy it lost gets released as a photon, careening out to our eyes so we can see it. When this energy is released, the amount of energy tells us what color of light we're going to see. So if we think about our visible light spectrum, we have red over here, right, Roy G. Biv. So we have red, orange, yellow, green, blue, indigo, violet. So on this side we have violet. Now remember, energy is related to frequency. So we have red, which has really big wavelength, really small frequency, so it's low energy. So if we're talking about the highest energy, right, between red and violet, because the middle ones we don't care, we want the extremes, right? Which color emitted corresponds to the biggest change in energy? It's going to be violet. Right? Violet is going to be the highest frequency, which means it had the biggest, the electron gave off or lost the most amount of energy. Now on the other side of that, when we start talking about things like wavelength, okay, wavelength corresponds to the lowest energy. So in this case, it would be red, right? Red would be our biggest wavelength. I like to think about red. I'll do it in the right color, right? Reds are kind of big, long, up and down waves, whereas this violet might be really short wavelengths, but high frequency. All right. So that's kind of gets us through the basic models of the atom, a little bit about light and how light is produced with the models of the atom. So let's talk about waves. Okay. So which type of wave travels faster, electromagnetic or mechanical waves? How do you know? Okay, so remember when we talked about electromagnetic waves, these are all types of light, right? So light waves travel at the speed of light, which is kind of obvious, right? Light travels speed of light, whatever. Mechanical waves, this is like sound, right? Sound is a mechanical wave, how you're hearing my voice right now. And it travels at the speed of sound. So, which one travels faster? Well, the answer is light. Light travels faster. The way I like to think about it is when you see a jet plane fly overhead, you're going to see it go by, right? So if this is you, you're going to see this jet plane go by before you hear it, right? You see it, and then the sound is kind of coming at you later on. Okay, so we see the jet plane, then we hear it. That's because light travels faster. And what is the speed of all light? Well, it is 3 times 10 to the 8th meters per second. I'd mentioned this in a couple classes. We haven't really looked at the number, but this is 3 times 10 to the 8th. That means it's a 3 with 8 zeros. It is fast, right? This is the universal speed limit for everything. Nothing can go faster than 300 million meters per second. And that is really, 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 really fast. Like, think about turning on a light switch. You don't even see the light approach you. It's moving so fast. It's just on or it's not. Okay, our 7 common types. All right, so I got a picture of our EM spectrum. So I'm going to scroll down here. So if we're looking at lowest frequency, we've got to remember that frequency and wavelength are inversely related. So that means if wavelength is big, our frequency is going to be small. Okay, so if we look down here at some of these numbers, right, 10 to the 4 and 10 to the 20. 10 to the 4 means a 10 with 1, 2, 3, 4 zeros after it, right? 10 to the 20 is a 10 with 20 zeros. 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. So obviously our frequency is way bigger over here than over here. Okay, so if we're ordering these from lowest to biggest frequency, we have radio waves. They're the smallest frequency, biggest wavelength. Microwaves. Infrared. Remember, infra means below, so right below red. So looking down here at our color chart, right, infrared is kind of below this red area. Then we have our visible light, our ultraviolet, which is higher than violet, our X-rays, and our gamma rays, which gamma rays are those very, very high frequency EM spectrum, EM radiation. Okay, so the highest energy, highest frequency, smallest wavelength, that's going to be our gamma rays right here. Woo! If we're talking about our lowest energy, lowest frequency, largest wavelength, that is our radio waves. And there's some implications there, right? That because of the really long wavelength and the low energy, they're really safe. That's why our cell phones use them. They can travel really far. So there's some good reasons why that frequency matters, why we really care about the frequency of these things. Okay, if we're talking just the visible spectrum, now we're only talking about light we can see. So from highest energy, well, if we look down here, right, our highest energy, so let's just look at these colors real quick. We can almost zoom in like right there, right? Our highest energy, and let's make sure we know, right, like about this area, I don't even know if my numbers are, we'll call it like this area, right? About there is going to be our visible light. So this is all our visible light. And so high energy is high frequency, so it's going to be over here in the violet section, right? Violet, purple, those are our really high energy, really short wavelength, really high frequency. Our low frequency, low energy, but really high wavelength is this red, right? Red is the high wavelength, really big wavelength, but the low frequency and low energy. So I can zoom back out. All right. Yeah, so that kind of covers the big ideas. The really important part, guys, is that we can look at a graph or a chart like this and be able to figure out what are the big wavelengths, what are the small wavelengths, what are the high frequencies, like over here, what are the low frequencies, and what kind of waves do those match up with. Remember, we have one of these in our notebooks we can use, so make sure you're flipping to the back page when you need to and looking at that in your notebook. Okay, mechanical waves are two different types of waves. These ones aren't too bad. The transverse wave is one that kind of goes up and down through peaks and valleys as it moves across, in the direction of the wave is to the right. The official definition is a wave that moves oscillates perpendicular to the direction of motion. So that means it's moving up and down as the wave moves to the right. Longitudinal is one that moves in the same direction as motion, that kind of oscillates in the same direction as motion. So that's that slinky where we get like the cramped together and then it spaces out and then it gets cramped together and then it spaces out. You can tell I'm great at drawing these, right? So this is our longitudinal wave. It's like a sound wave, right? We can also think of it as kind of like moving out like that, a sound wave. But light is that transverse wave, sound is a longitudinal wave. The big difference between the two is that waveform, right? Is that the transverse wave has these up and down waves, where those longitudinals have the compression and the rarefaction. We can still have wavelengths and amplitudes and all that with both of them, but for our most part, when we talked about the details, we talked in terms of a transverse wave. Okay, maybe know some examples of each one, right? Transverse, biggest example is light. Longitudinal, biggest example is sound. And so we have those two different types of waves. And we can have non-light. We can have like an ocean wave where you take a jump rope and flip it with your hand, and as that wave moves across, that's a transverse wave as well. All right. Okay, last but not least, just some terms we need to know. Wavelength, I'll draw some pictures for these. Right, wavelength is just the distance between two waveforms, so kind of this peak-to-peak distance. Right, and remember, it is measured in meters or nanometers or centimeters. Right, it's a wavelength, or it's a distance. So it'd be peak-to-peak, or it could be like trough-to-trough, or I guess crest-to-crest, or here to this area. Right, so it's the easiest way to just measure peak-to-peak. Medium doesn't really get a picture. Medium is just what the sound is traveling through. Okay, so the medium for a sound wave is air. The weird thing, the medium for light is the photon. So the particle is the medium. That's why it can travel through vacuums and all of that. Okay, frequency is the cycles per second. So how many times it goes up and down in 1 second. And so if this was 1 second, this would go through 1, 2, 3 cycles per 1 second, or a hertz, or that would be 3 hertz. Okay, the period is the inverse of frequency. So if you take 1 divided by your frequency, you get your period. And the period is just how long it takes it to do 1 cycle. Okay, so if we have some wave like this, whatever, right? The period is the time it takes it to go from there to there, right? From here to here, the time it takes it for one wave, for a point on one wave to pass through and come to the same point on the next wave. That is your period, right? How long, how much time goes by for one waveform to go by. And last but not least, we have, oh, that's going to be huge. We have our amplitude, which is just the height of the wave. That's a horrible line, but it is just the height of the wave. How tall the wave is, that is our amplitude. All right, guys. If you understand that pretty well and you feel comfortable with that, you are ready for our Unit 1 assessment. Remember, this assessment's worth a lot of points. It can really help or hurt your grade. So make sure you're studying for it. Make sure you have this study guide filled out, that you've gone back and you've organized your notes. If you haven't taken great notes off the like the models of the atom or the wave notes, go back, watch the videos, take notes, right? A good way to study is just to go back and watch those videos again, and you could even take notes again. Those are all great ways to study. Yeah, this is kind of a short unit, so there's not a ton of information, but it is all kind of new and obscure information. So make sure you're studying it, you're getting ready, and yeah, I'll see you next class when you're ready to rock the test.